So for my PennCast assignment, I got a homework problem from homework number 2 on the Doppler effect. It says, a physics instructor is whirling a 600 Hz sound device overhead in a circular motion of 100 revolutions per minute on a 1.0 meter long rope. What are the highest and lowest frequencies observed by the class? So I went ahead and drew a picture of a professor whirling around a sound device overhead in front of the class. So let's go ahead and fill in some values here. So we have a 600 Hz sound device. So we can write 600 Hz out here. 100 revolutions per minute. And on a 1.0 meter long rope. And it says, what are the highest and lowest frequencies heard by the class? So we know we have a Doppler effect problem because we have a moving sound device and a stationary observer. So for a moving device and a stationary observer, we know that our toolbox of equations, we are going to need to use F plus and F minus. The F plus would be F naught over 1 minus V sub S over V. And then the F minus would be F naught over 1 plus V sub S over V. So let's go ahead and figure out what we know so we can figure out what we don't know. So in this equation, we know F dot, which is the frequency of the sound device, so, or the frequency of our source. 600 Hz. We know the velocity of V, which is just the speed of sound. So assuming our physics class is at room temperature, we can say 343 meters per second. We need, obviously, the F plus and the F minus, but what we're missing from this equation over here is V sub S. So I'm going to go ahead and solve for V sub S first so that I can just easily plug it into both of these equations. So V sub S means the velocity of our sound device. So our sound device is traveling in a circular motion with a radius of 1, so we can't really just use like 100 revolutions per minute. We have to convert it to an angular velocity. So our V sub S will be an angular velocity, which would be our radius, or our 1.0 meter long rope, times our angular speed, which is 100 revolutions per minute. I'm going to need to convert the revolutions into radians. So we know we're going to do 2 pi radians per revolution. So now I have these revolutions canceling out. If I did my final answer now, I'd get meters per minute, but I know I'm going to want meters per second so that I could easily do this division problem over here. So I'm just going to go ahead and convert it now, for 1 minute being 60 seconds. So then my minutes cancel out, and I'll get my final answer in meters per second, as desired. I went ahead and did this calculation on my own, and it is 10.47. We have 2 degrees of certainty dictated by our rope length, so we get to report this as 10 meters per second. So now that we have our angular velocity, or V sub S, in terms of this equations, we can go ahead and solve for the frequency of it while it's approaching and the frequency of it while it's receding from us. So let's start with the frequency of while it's approaching would be F naught, or the frequency of the device, so 600 Hz, divided by 1 minus v sub s, which we found to be 10 meters per second, divided by v, which is 343 meters per second. Our meters per second cancel out, and so we know we're going to get our answer in hertz as desired. So if you carry out this calculation, you will get 618 hertz, but we only get two significant figures, so it will round up to 620. Now the frequency, the observed frequency as the object is receding would be this equation here. So we still have the F naught, so 600 hertz, divided by 1 plus the velocity of our device, so 10 meters per second, divided by the velocity of sound, so 343 meters per second. Again, those cancel. Well, the units cancel, sorry. And we get 583, or with two significant figures, we get 580 hertz. So as the sound device is approaching us as a class, it makes sense that we would hear a higher frequency than the professor hearing the source. So this would be the highest frequency. And as the sound device is receding or away from us or behind the professor's head, it makes sense that we would hear it as less than the source. So 580 hertz is the lowest frequency observed. So yeah, there's our final answers.